Okay, so welcome to the course again, Fundamentals of Solar Photovoltaics and Technologies. So in this lecture today we will learn about intrinsic and extrinsic semiconductors, having learned the basics of semiconductors, how semiconductor materials have presence of bands, and we also looked at the reasons behind that. So just to recap, we looked at the process to determine carrier concentrations, and this is important because when you want to determine conductivity, conductivity is a product of carrier concentration multiplied by electron charge multiplied by the mobility, and same for hole. And to determine these we need carrier concentrations in the bands. So carrier concentrations, there are two types of carriers in semiconductors, intrinsic semiconductors, as we saw. First is electron, second is hole. Electron is the charge carrier in the conduction band and hole is the charge carrier in the valence band. So number of electrons per unit volume in the conduction band, that is Ne. So in this case we can write this as Ne, or sometimes it is also written as N, and here we have written for holes per unit volume in valence band, sometimes it is written as P, but we can also write it as NH. So for the sake of continuity in the previous in the subsequent lectures, we can write this as Ne and NH, that is more appropriate, NH and Ne. So carrier concentration in a given band is determined as product of probability of occupation multiplied by the density of states in that band. So dE is the density of states, so this is dCe in the valence band, and Fe is the electron probability of occupation in those energy levels, and this is integrated from Ec to infinity, the edge of the conduction band, that is bottom of the conduction band, until higher states. Likewise, the hole concentration is calculated as is determined as probability of finding a hole, which is 1 minus Fe. So this is Fhe, if you like, you can write it as, and multiplied by dE, this will be dVe, which is the density of states in the valence band, integrated over minus infinity to Ev, that is the until the upper edge of valence band. So Fe is the fraction of states occupied at T for electrons, or probability of, you can say, the occupation of these states, and 1 minus Fe will be the analogous term for holes, and dE is density of states per volume per unit volume per energy interval dE, and C is for conduction band and V is for valence band. So now we will take this forward and we will first see what these things are. So let us first see what the density of states for conduction band and valence band they are. So again you can write dCe and dVe, here it becomes dVe. So dCe will be 1 over 2 pi r 1 over 2 pi square into 2 Me star divided by h cross square to the power 3 by 2. Instead of e to the power half, we have written E minus Ec to the power half, because we are looking at energy levels from Ec onwards. So Ec becomes the baseline for this. It is not from 0 to E, it is from Ec to higher energies. And for valence band, the analogous term dVe is 1 over 2 pi square into 2 mh star divided by h cross square to the power 3 by 2 into Ev minus E to the power half. So this is how now these derivation of these you can see, you can go through in solid state physics by KANPUR-NPTEL. Or electronic properties of materials by Hummel. In both of these books you will find the derivation of density of states, which is pretty straightforward. Okay, we did that to some extent in the last class. So having determined this dC and dE, you then plug these in the previous equation, and we also know the term for Fermi probability. Fermi probability is nothing but 1 over 1 plus exponential E minus EF divided by KBT which can be simplified using Boltzmann approximation if E minus EF is greater than, especially if Fermi level lies far away from either valence or conduction band, then this can be this term can be taken in the numerator. We are not going to do all the maths of derivation, which is pretty straightforward. You can go through these books to do that, but when you plug in these, what we determine is n is equal to nc into exponential EF minus EC divided by kBt, where nc is 2 me star kBt divided by 2 pi h cross square to the power 3 by 2, and p is equal to nv into exponential of EV minus EF divided by kBt, where nv is similar to nc except that me star gets replaced by mh star. So what are nc and nv? Nc is the effective density of states in the conduction band. What it means is that as if all the states were located at a value called EC, sorry, it should be, and in case of EV, it should be EV. So Nc and Nv are effective density of states in the conduction band and in the valence band, and these could be construed as if all the states were located either at EC or EV. So essentially you can see that Nc and Ev are parameters only of function only of temperature. As you see, the temperature term appears here, except that the constant, and that to the power 3 by 2, but the stronger dependence on temperature comes from this exponential term, where concentration of electron or hole is proportional to exponential of EF minus EC by kT or EV minus EF divided by kT. So this exponential dependence is a dominant dependence as far as carrier concentration is concerned. So for intrinsic semiconductors, because we create one electron, so when you excite this electron from valence to conduction band, for every electron we create one hole. As a result, so this excitation from here to here, so for E is equal to H plus. So basically we can write N is equal to P or Ne is equal to Nh. I will replace here this by Ne Nh. So this Ne into Nh is equal to Ni square, and this is equal to Nc into Nv exponential of Ec minus Ev divided by kT, or you can write this as N is equal to P is equal to Ni, because Ec minus Ev is nothing but Eg. I can replace this as N is equal to P is equal to Ni is equal to square root of Nc and V into exponential of minus Eg divided by 2 kT. So you can write it the way you want, but this is a more general way of writing. So you can see that N and P are exponential functions of band gap. This is your band gap, and this is temperature. So here it is square root of Nc and V, and T to the power, basically you can say both of these are function of T to the power 3 by 2. So there will be 3 by 2 dependence there, but the more important part is this exponential dependence. So hole and electron concentration in an intrinsic semiconductor will be equal in concentration. First, this is equal to Ni, we can write this as Ne or Nh, and that the band gap and temperature affect these concentrations very profoundly. So there is an exponential dependence on each of these, and that is why when semiconductors band gap increases or decreases, there is a large change in the concentration of carriers. Secondly, when temperature changes even by a small amount, there is a large change in the carrier density. And this, as we will see, is strongly related to, because we see that sigma is equal to Ne mu plus Nhe mu h. So this we will see that mobility also has a temperature dependence, but that is not an exponential term. So as a result, this Ne dependence and Nh dependence on temperature, it makes basically as if sigma is also exponential of minus Eg divided by 2 kT. So as a result, and the conductivity of intrinsic semiconductor also happens to have exponential dependence on temperature. So if you plot log of sigma versus 1 over T, you will see that it is pretty much the case. So, you can determine from the slope of this plot the band gap, and this tells us that the other temperature dependence is much weaker as compared to exponential dependence. From this we can also determine the work function. Work function for a semiconductor is another important, this is actually another important property. So, work function is nothing but the difference between the Fermi level and the vacuum level. See, just like metals have work function which is determined by difference between the vacuum and Fermi level. Similarly, for semiconductors we determine work function as the difference between the vacuum level and the Fermi level. And one must also remember Fermi level is like a potential energy. So, when a semiconductor is in thermal equilibrium, delta EF must be equal to 0, which means Fermi energy should be throughout the material same, they should not change at all. So, even though material may have differences in composition or something else, but as long as it is in thermal equilibrium, Fermi level will remain constant. The bands, the relative position of the other bands, conduction and valence band with respect to Fermi level may alter, okay, but it is the Fermi level that will remain the same throughout the crystal in the state of thermal equilibrium. So, in summary, what we have done so far is to look at carrier density in semiconductors. Carrier density in semiconductors is, so if I write this as Ne or NH, so Ne is equal to F integration of Fe dCe over a energy range of Ec to infinity, and NH is 1 minus Fe dE dVe integrated over minus infinity to Ev. From these we can determine what are Ne and NH, and these are nothing but exponential functions of differences in the Fermi level and the conduction band energy, or Fermi level and the valence band energy divided by kT, and they give us a strong dependence on temperature and the band gap. And we know that for an intrinsic semiconductor, the Ne is equal to NH, which is equal to Ni, and this is equal to nothing but the square root of NC/Nv into exponential of minus Eg divided by 2 kT. We can also plot, now you can revisit the plot that we made earlier. So, on the y axis we have energy, on the x axis we can plot dC or dV, or we can say, and here we can plot Fe. So, if this is your EF, and let us say okay, this is EV, this is EC. So, we can first plot, if this is 0, this is 1, let us say this is half, the Fermi function will go like this, okay, this is 1, okay, and then we can plot the density of states. Density of states will change like this, in this fashion on both sides, and accordingly we can make the carrier density for electrons will be there like this, and for holes it will be like this. So, this is N, this is Ne and NH, and this will be, red curve will be dCe, and this will be dVe, and this black curve is nothing but Fe, okay. So, and these lobes will, so dC and dV will remain constant, pretty much the same. When you change the temperature, the Fermi function will change. As a result, the lobes of Ne and NH will, so as the temperature changes, this will become bigger, because your, it will go like this, okay, because your Fermi function will also become like this, okay. So, that is how your carrier concentrations will change as a function of temperature. So, this is at T1, this is at T2 greater than T1. All right. So, you can determine carrier concentrations. So, for example, you can take this as a home exercise. Let us say silicon band gap is 1.1 electron volt, temperature you consider as 300 Kelvin. Then as a homework you can take, determine the of intrinsic carrier in silicon. Silicon band gap is 1.1 electron volt, temperature 300 Kelvin, and any, you will find that the answer is approximately this. Okay. So, this should be your answer. They are very small. You will figure out that they are very small as compared to number of atoms in silicon. Number of atoms in silicon are 10 to the power 28 per meter cube, and this turns out to be 10 to the power, you can say 10 to the power 16 per meter cube. You can see there is a 12 orders of magnitude difference. So, we can see that only so many number of bonds are broken. Okay, not all the bonds are broken. So, it is only a small so it is only a fraction of bonds that are broken. So, you can easily calculate that number of bonds that are broken are approximately 10 to the power 16 divided by 10 to the power 28. This will be the fraction 10 to the power minus 8. So, numbers look large, but in terms of relative magnitudes, these carrier concentration are very small as compared to number of atoms, because each atom can contribute, each atom is bonded by 4 and each silicon atom is 4 plus, right. So, they share 4 of these electrons, and as a result Ne is equal to Nc, and so I need to make a change here, Ne and Nh. So, Ne is equal to Nc exponential minus Ec by Ef by Kt, and Nh is equal to Nv exponential of minus Ef minus Ev divided by Kt. Just note down the sign difference. Here Ec minus Ef with a minus in the bracket, and here it is Ef minus Ev, because here we are going down in the energy, here we are going up in the energy. So, Ec is higher than Ef and Ev is lower than Ef, and we know that Ne is equal to Nh, and hence so we can say from this we can also determine what is the Fermi level for an intrinsic semiconductor. Let us say intrinsic semiconductor's Fermi level is EFI. So, by equating these two, I can get the value of EFI, which is EFI is equal to Ec plus Ev divided by 2 plus Kt divided by 2, it should be Kbt divided by 2 into ln of Nv divided by Nc, or you can write this as in terms of effective masses, because the only term that is different between the two is effective masses. And if these two were same, you can see that if Mh was equal to Me, then basically EFI will be equal to Ec plus Ev divided by 2 if Me star was equal to Mh star. So, basically what it means to say that if this condition is fulfilled, then Fermi level will be mid gap. But often this is not the case, because there is an effect of temperature, there is also a difference in Fermi energy, there is a difference in effective masses. Fermi level as a result may be a little bit off from the exact center of the band gap. So, we assume normally for a given semiconductor Fermi level is right in the middle. Okay. So, this is our Fermi level, but it may change its position depending upon temperature and the effective masses of electrons and holes, the magnitude of those. Okay. So, so for any semiconductor we have seen that Ne is equal to Nc exponential Ef minus Ec by Kt, and Nh is Nv exponential Ev minus Ef divided by Kt, and N is equal to Np, Ne is equal to Nh is equal to Ni. So, Ni is equal to Nc exponential. So, you can write these expressions in different ways. So, for example, I can write Ni as Nc into exponential of EFI minus Ec by Kt, which is equal to Nv into exponential of Ev minus EFI by Kt, and then I can also write what is Nc and Ni. Nc is nothing but Ni into exponential of Ec into EFI, Ec minus EFI by Kt, and Nv is Ni into exponential EFI minus Ev by Kt. So, from this I can determine what is Ne and what is Nh in terms of Ni. So, we can see that it turns out that Ne and Ni, Ne and Nh in terms of Ni is differentiated, is the differences of this function exponential Ef minus EFI divided by Kt. So, normally we take this as 0, right. For ideal case, this will be taken as delta Ef. So, that is Ef minus EFI is taken as 0. So, which means Ne is equal to Ni and Nh is equal to Ni, but if there is a slight difference, then we can see that this will make a little difference. And this also allows you to calculate for an impure semiconductor the concentration with respect to Ni, because when you make an impure semiconductor, the Fermi level changes. For an impure semiconductor, as we will see later on, these two change a lot, and from these relations we can determine what is the concentration of electrons in those semiconductors, and we can determine basically various properties from these relations. One thing which we also have to remember, that since Np is equal to Ni, N dot P is equal to Ni square, the product of electron and hole concentration, that is, or Ne dot Nh must be equal to Ni square. Okay. So, this is something that we will have to remember, because this is true in case of any semiconductor, no matter what it is, whether it is a pure semiconductor, impure semiconductor, does not really matter. So, in case of intrinsic semiconductor, as I said, intrinsic means pure semiconductors. The conductivity increases with temperature in a logarithmic fashion, and behavior is opposite to metals, and we know that Np, Ne is equal to Nh is equal to Ni is equal to square root of Nc Nv exponential minus Eg by Kt, and sigma is equal to Ne into Nh into E mu h, such that so together, if you do that, if you put in the terms, sigma undoped is approximately proportional to exponential of minus of E gap divided by 2 Kt. So, which means if you plot this, if you plot ln sigma over 1 over T, we should get this kind of Arrhenius behavior, and slope of this will give us minus Eg by 2k. Okay. So, essentially, and if you look at the band gaps of materials, silicon is 1.1 eV. If you look at germanium, germanium will have 0.67 eV, and things like gallium phosphide will be 2.25 eV. So, slope of this plot will vary depending upon the type of semiconductor. For something like gallium phosphide, the slope will be like this. For something like germanium, the slope will be like that. So, this is, so crossovers may be at different points. So, this is germanium, this is silicon, and this is gallium phosphide. So, basically, as you move towards higher band gap semiconductors, so as Eg increases, your hopping probability decreases, and hence sigma decreases, because your n value decreases. So, as band gap goes up, your number of electrons which can cross from valence to conduction band, the probability of that reduces, as a result the conductivity reduces. Secondly, as the temperature increases, your conductivity again goes up in the logarithmic fashion. So, what we have done is we have learnt about the temperature the carrier concentration determination of intrinsic semiconductors. So in summary, what we have done is we have determined we have seen how we can determine NE and NH, how they are related to NI, what is difference between EF and EFI, and how the conductivity varies as a function of NI and temperature. Okay. In the next class, what we will do is that we will see that why do we, but semiconductors are often not used as a pure semiconductor, they are often used as impure semiconductor, which are called as extrinsic semiconductor or impure semiconductor. So, we will see what is the need of that and how do their properties depend upon various factors. So, we will do that in the next class. Thank you.